Hello everyone, my name is Thomas, a PhD student and senior at the University of Oslo. Today I'm glad to have these opportunities to present our work as a journal first paper here. This work is about modeling foundations for testing self-healing cyber-physical systems. And I will introduce this work from these three parts. First, I will introduce background information and then show details about the modeling foundations, and last present the evaluation results and conclusion. So first, let's see what are self-healing cyber-physical systems and uncertainties, and how we propose to execute the system. As we know, cyber-physical system is the integration of communication, computation, and control. It uses sensors and actuators to monitor and control some physical processes. During this process, software or hardware fault may occur at runtime. To increase dependability, several physical systems are equipped with self-healing behaviors that can detect the fault and apply a proper adaptations at runtime to recover the system from the fault. We call this kind of system as self-healing cyber-physical systems, in short SH-CPS. Besides recovery, SH-CPS have to handle various uncertainties, such as measurement errors from sensors and actuation deviations from actuators. The objective of our work is to test if an SH-CPS can still behave as is expected under the uncertainties. This is a challenging task because the fault may occur at any time, and there are numerous possible combinations of uncertainties. It is infeasible to cover all scenarios, and to effectively detect fault, we proposed an executable model-based testing approach. In this approach, we use a test model to capture expected behaviors of the SH-CPS under test. We execute the model together with the system and simulators of sensors and actuators. By introducing uncertainties via the simulators and sending the same operation invocation to the test model and the system, and comparing their consequent state, we can dynamically test the system against the test model. And with an intelligent algorithm, we can learn how to choose the operation invocations and uncertainty values to effectively detect fault. To realize this approach, first we need to understand clearly what are SH-CPS and uncertainties. And then we should know how to specify the expected behaviors and uncertainties for SH-CPS. And when the test model is ready, we need to know how to execute the model together with the system and simulators. And the answers to these three questions correspond to three modeling foundations, which are to be introduced next. So now let's see the conceptual model first. A cyber-physical system is a collection of heterogeneous and distributed physical units, and each physical unit has one or more controllers that use sensors and actuators to control some physical processes. A controller has two kinds of behaviors. One is functional behavior, that is to fulfill some business requirement. The other is self-healing behaviors that help functional behaviors to achieve their goals even in the presence of fault. The self-healing behaviors can be further decomposed into self-diagnosis and self-recovery. For self-diagnosis, it is responsible to detect fault from measurement produced by probes. And when a fault is detected, self-recovery decides which adaptation actions to take to recover the system from the fault. For self-diagnosis, it can be realized either based on prior domain knowledge or based on historical data. In the first case, qualitative or quantitative knowledge can be expressed as a quantitative or qualitative model that can be used to identify the fault. On the other hand, we can train a fault classifier based on historical data and use this classifier to estimate when a fault has occurred. For self-recovery, it can use action policy, goal policy, or utility function policy to decide which adaptation action to take. And it can use three kinds of effectors to change parameters, system architectures, or control logics and runtimes to recover the system from a detected fault. Regarding the uncertainties, it is associated with uncertain features. For instance, uncertainties could be we don't know the exact value of a measurement error, and the measurement error is the uncertain feature. To specify the uncertainty, we first need to capture all possible values of the measurement error, and the set of all possible values is defined as the universe, and each possible value is defined as a data. Sometimes we only have qualitative knowledge of the uncertainties. For instance, we can only describe the measurement error as high error or low error. In this case, each qualitative term is defined as a category, and we can use a membership function to capture the belonging relationship between a datum and a category. And we can use either probability measure or possibility measure to specify the likelihood of a possible value or category. Now we know what are SH-CPS and uncertainties. Based on the conceptual model, we developed 4 UML profiles and modeling methodologies to specify the test model for testing SH-CPS under uncertainties. Now let's see how can we use the profiles to specify a test model. First, we use UML class diagrams to capture system component and structures. In the component profile, we provide 6 stereotypes that can be used to identify the roles of each component. For each component, we use UML state machine to specify their expected behavior. In the behavior profile, we provide the stereotype of fault and error to specify how a fault is expected to affect a behavior, and where the attribute of this fault stereotype, we can also specify an operation that can be used to inject the fault to trigger a corresponding self-healing behaviors during testing. For self-healing behavior, we provide the stereotype of monitoring state, fault identified state, and adaptating state, where the transitions between monitoring state and fault identified state, we can specify the logic of fault detections used by these self-healing behaviors, and where the transitions between fault-identified state and adaptating state, we can specify the recovery policies used by the behavior. And for the state defined in the state machines, we should also specify a constraint of state variable values. This constraint should always be satisfied by the system when they are in a corresponding state. By evaluating this constraint during testing, we can strictly test if a system behaves as expected. And for uncertainties, we provide an uncertainty stereotype together with 3 data types. The universe and the category data type enable us to specify all possible values and categories. And the measurement data type enable us to specify a probability or possibility measure for the uncertainty. And last, we provide the testing profile to model the testing utilities. Here we provide the test component stereotype that can be used to identify a component that is to be simulated, and where the configuration attribute of this stereotype, we can specify the configuration of the simulator. And we provide 2 stereotypes to identify 2 kinds of operations. The check property action can be used to query state variable values from the system under test, and the create stimulus actions can be used to control the behaviors of the system. And for each operation, we also need to specify their methods where an activity diagram. In this method, we need to specify a testing interface corresponding to this operation defined in the model. Now we know how to use the profiles to specify the model. Next, we need to execute the model with the system and simulators. But first of all, we need to know how to execute the test model. Here, the standard of FUML and the precise semantics of state machines and our extensions provide semantics for each model element used in the test model. Based on the semantic, we can execute the test model in a deterministic manner. Next, since the test model and the system and simulators are implemented with different modeling paradigms, they may have different time semantics. And to enable the co-executions of hybrid model, we use the standard of functional mock interface. It provides us a standard way to co-execute the hybrid models. Based on this standard, we implemented the TM-Executors. First, there's an execution engine in the TM-Executor that takes executable test models as input and executes the model together with the SH-CPS under test. During execution, a test driver chooses operation invocations that can be used to trigger transitions defined in the model, and change the state of the system on the test. When an operation invocation is performed, the execution engine obtains state variable values from the system and uses a constraint checker to evaluate the constraint defined in the test model with the state variable values. When a constraint is violated, then it means a fault is detected. Otherwise, the execution engine will keep on the execution until a terminal state is reached. Meanwhile, an uncertainty introducer chooses the value for each uncertainty and use the uncertainty values to modify input and output values of the simulators to simulate the effect of uncertainties, so that the TM-Executors enable us to directly test SH-CPS against a test model under uncertainties. To evaluate the conceptual model and the modeling and testing framework, we first check the correctness and completeness of our conceptual model by mapping concept from live case studies to the concept defined in the conceptual model. And the results show that the conceptual model managed to cover all concepts from the case studies. Next, we managed to specify 3 test models for 3 case studies using our modeling framework. It demonstrates the applicabilities of the proposed profile and the modeling methodology. And last, we applied TM-Executors to test SH-CPS against a test model. And the result shows that the overhead of executing the test model together with the system is very, very small, so that it is feasible to apply TM-Executors to test SH-CPS. So in conclusion, in this work, we proposed a conceptual model to understand what are SH-CPS and uncertainties. And based on this conceptual model, we provide a set of UML profiles and modeling methodologies to specify a test model. And we also provide a TM-Executors that can execute the test model together with the SH-CPS on the test and the simulators of sensors and actuators to enable the executable model-based testing approach. In our following works, we have applied reinforcement learning algorithms to choose operation invocations and uncertainty values to effectively detect fault, and it has shown promising result. Okay, that's all for the presentation. Thank you for your interest and time.